What's up, everybody? Welcome back to another weekly live stream from Scalar Learning, where we cover questions from Khan Academy's SAT Math section. So today we are continuing with past table data, and we're going to Scatterplots level 2. And as always, I'm seeing these problems for the first time. So without further ado, let's get into it. Here we go. The scatter plot drawn at left shows the amount of water vapor Y in grams that will saturate 1 cubic meter of air at sea level for different temperatures in degrees Celsius. So let's see here. So this is the air temperature, and this tells us how much water, this tells us the water vapor saturation levels. And so as the temperature rises, more water vapor, right, will saturate 1 cubic meter of air at sea level. All right, cool. So now we have this function that represents that. What is the value 4.19 in the model tell us about the amount of water vapor that will saturate 1 cubic meter of air at salt level? So x is, so let's see. So 1 cubic meter. So the y is our cubic meter. Sorry, it's the, here we go, water vapor level. Okay, so 1 cubic meter of air at sea level. Sorry. Okay, so here we go. At sea level, now we're talking about the, oh, wait a minute. That's the temperature. Okay, hold on. Let me read this again. The scatter plot at left shows the amount of water vapor in grams that will saturate 1 cubic meter for different temperatures in, okay, 1 cubic meter of air at sea level, but we don't know what does sea level have to do. Oh, I see. All of this is at sea level. Now that's what threw me off. I got it. Okay, so it will take approximately 4.19 grams of water vapor to saturate the air. Yeah, it's A. But I'm going to tell you why in a second. Let me just read the rest of these. Take exactly. Oh, no, not approximately. Is this approximately? Or no, this is exactly. Hold on. Right? It's one of these two, and I'll tell you why. So basically, these two are talking about rates of 4.19%, and that's not what is on the y-axis. Now, when x is 0, that's going to be 0 degrees. And so what happens is when you have 4.19 times 1.07 to the 0th power, okay, this basically means that 0 is the temperature. Anything to the 0th power is just 1. So we will get a value of 4.19 at 0 degrees. So the question is, that my only question is it exactly or is it approximately? Now that's my last little tricky bit. I'm kind of want to go with exactly, because if we plug it into this function, that's what we're going to get is exactly 4.19 grams of water. The only reason why I'm hesitating is because if we say approximately, because this is a scatter plot, this is just one piece of data, so it definitely could be approximately. Let's go with exactly, and let's see what their answer is here. Okay, it's approximately, and let's see what the explanation is. So model in this function, okay, in this context, so why does it say? The choice is incorrect because the line, oh, got it. That's right, that's right. This is our line of best fit. That's what I should have been thinking. So they didn't say line of best fit, so they said a function that models the data is shown. So it is actually approximately. That's the thing with scatter plots and the functions. The functions are just meant to be really good approximations, but approximations nonetheless. All right. So like I said, that can happen. Looking at these problems for the first time, I do make mistakes occasionally. Next, let's go to question number 2. The scatter plot to the left shows information on organic food sales in the United States from 2005 to 2012, where X represents years since 2005. Okay, so this is like 2006, 2007, 2008. All right, and Y represents total sales in billions of dollars. Okay. Which of the following equations best models the relationship between the number of years since 2007 and the total organic sales of food? So this is interesting because now they said since 2007. Okay, so that means when x equals 1, or sorry, when x equals 0, we should be at this 2007 mark. So let's see, which one of the, where is it at 2007? We should be around like 21 and 0 since 2007. So which one of these, right? Where X represents years since 2005. Okay, now let's take a look here. So 0. So if this is 1 year from 2007, right? We should be getting, this is 2005, 2006, 2007. So 0 should give us a value of 20.1. I wonder if that's almost a typo because out of the blue, 2.7 comes up here, right? I wonder if that's a mistake. Okay, let's see if I can get a little bit of a better idea. And what's my slope here? My slope is like, I'm going from 15 to 30. Okay, so I'm making a positive change of 15 over, let's say, 6 years. So I should have a slope of approximately 5, right? Did I do that right? 15 to 30. So 15 up and 6 to the right. So I'm looking at a slope of 5, but I don't see any options with the slope of 5. So hold on, let's see here. From here, 20 to 30, so that's 10 over 4. Okay, that looks more accurate. 10 over 4, which is about 2.5, which is why I'm leaning towards this guy. The only issue with this is, so this seems like this makes the most sense, right? This is a good slope. These slopes don't make any sense. They're too big. So this is a good slope. This slope is too small, all right? And the only problem is with this 2007, I'm almost wondering if that's a typo. Let's see if this is right. Okay, so that's correct. But if you're saying years since 2007 and you actually plug in 0, that should be the 2007 value, which should be 21. So I think they made a mistake, and I think this is meant to say 2005. And let's just see in the answers. Yep, so they calculated that 2.5. Okay. All right. So anyways, that is our answer. Let's move on to the next question. Scatterplot shows the cost to run a 30-second advertisement during a major sporting event from 1970 to 2010, where X is years since 1970 and C is cost. So we have cost here and years since 1970. An exponential function that models the data is shown above. Based on the model, which of the following is a true statement? The cost to run a 30-second advertisement during the sporting event in 1970 was about 1.1 million, or sorry, 1.1 million. So again, at 0, this is 1970. So let's see. 0, it's about 1.1. That doesn't look right. It looks more like 1970, we're talking maybe 100,000 or maybe 70,000, right? This is 200,000, 400,000, so that doesn't look right. The cost to run a 30-second advertisement during the sporting event was 1.1 million in 2010. So that's where X equals 40, okay? And so, because X equals 40, that's 40 years from 1970, that's 2010. We don't really even have a data point. This is the best we can do right here, but actually our real data point would be up here, almost like 4 million, because if we're talking about in thousands of dollars, this is 200,000, this is our million point. So 2010 doesn't look right. So this one I'm going to cross off as well. Between 1970 and 2010, the cost to run a 30-second ad increased by 110,000 each year. There's no way, if this is an exponential function, it's growing. The amount that it increases is not constant, right? So you can say, I mean, we could do an average and say from 100,000 all the way up to 3 million divided by 40. So I mean, I can do that calculation, but I don't know if that doesn't sound good. So let me look at this. The cost to run a 30-second ad sporting event increased by about 10% each year. That makes more sense. So let's see here. So we're talking about 200,000 and then maybe going up there. I feel like this makes most sense. these are hard questions. So the only thing I'm going to do is I'm going to say, if we go from a change of like 3 million, let's say, right? 3 million divided by 40. I just want to see what this comes out to be. 3 million divided by 40. It's about 75,000. So we could say, but this looks better because a percentage, that's going to be like an increase. So I imagine they're looking at some sort of an exponential function, which with a percentage increase makes more sense. Yikes. There's not great data to test this out. Let's go with it and see what we get here. Okay, that's cool. And then let's look here. Yeah, so this is a constant rate of change, right? So it's not an exponential thing. Yeah, so that's why they did choose 10%. All right, let's move on. Next, the scatter plot to the left shows the population of Florida in millions from 1900 to 2010, where T represents years since 1900. Which of the following exponential equations best models the population of Florida from 1900 to 2010? So now you can see that this looks definitely exponential. Linear would be just a straight line, but because it's got this curve to it, where it's like shooting up here, that's an exponential function. The thing is, all of these are exponential, so that's fine. Now, this is a calculator problem. So how can we test this out? How can we figure out what's going on? First of all, it cannot be A or B, because A or B, since this value is less than 1, this is actually going to decrease. This is a decreasing function like that, because that's just when it's between 0 and 1, it's just going to be decreasing. And this is increasing. Clearly, it's getting bigger and bigger as we go farther. So A and B are out. It's now between C or D. I'm already going to kind of assume that this just looks like this is such a big increase every year, 1.4, and they've got the same starting point at 0.53, right here at 0, so that's fine. But I'm assuming it's going to be this one. Now the way that I'm going to verify this is I'm going to plug in a value for T. Like I'm going to plug in 90, and what I should get is about 13 million, right, for this answer. So let's plug that in. So 0.53 times oh, we don't need that. Times 1.035 to the 90th power equals, and we should get around 13. Oh, did I do this wrong? 11.7. Oh, here we go. Let me try that again. Oh, maybe that is the wrong one. So let's try the second one. I think I did it correctly. So let's try this one instead. 1.41 to the 90th power. Okay, this is right? 13 digits. So it's about 14 million or something. Oh, wait, no. No, this is 13 zeros. This is huge. Okay, let me try that last one more time. 0.53. So let's do, okay, 1.035 to the 90th power equals 22. So this is actually, so this is a 3% growth rate, but it's way too small. You see, as this is growing, oh, no. This is right. This is right, because this is in millions. I was thinking we should get 13 million. No, we shouldn't. We should get something like this, 22 million or whatever. It's got to be C. That's what, I wasn't thinking that the answer's coming back in millions. And that's exactly right. Okay, let's go on to the next question. Last question. The owners of the teams in the National Football League have developed a trade value chart which assigns a numerical value to recently drafted players. Draftees with the highest numerical value are considered to be the most valuable on the trading market. For example, the number 1 draft pick is worth 3,000 draft points and can be traded for picks 2 worth 2,600 and 50 worth 400 points. Okay. Scatter plot to the left depicts the trade value F in points of draftees based on their draft number X. Which of the following functions best describes the relationship shown? This is a lot of information. I think we can kind of look at this function without even having to deal with all of that complexity and kind of figure it out. Now again, remember I said the shape of an exponential function, when it kind of comes down like this, we know that this value in here has got to be between 0 and 1. Like, this is crazy to have a number that you'll never have a number. I mean, you could, but you'll rarely have a number that big inside that piece where you're having an exponent applied to it, because you just raise it to the second or third power, it's going to be massive, right? And look, this is getting closer and closer to 0. This one could be, right, because it's below 0 and 1. I'm not sure if that looks like a fast enough decrease. So this is again over 1, so this is out. So it's either between B or D. Now, the cool thing is we kind of know that our 0 point has to be right around 3,000, right? So when we plug in X, this part will turn into 1, and we'll get whatever remains, whatever's up front here. And so look, 3,000. This one has to be just based on that X-intercept. I'm sorry, based on the Y-intercept. If you want further verification, you could try and plug in some numbers, like we could try and plug in, let's say 120 into this equation, let's say. So we'll say 29, this is calculator, right? 2900.65 times 0.96 to the 120th power, right? Equals, yeah, and that looks right? Like we're down here. We don't really need to test that. All right. That is it for the weekly live stream from Scalar Learning. I hope that was helpful. If you did find it helpful, please leave a like below. It really helps out. And if you want to see more of this content, make sure to subscribe to get SAT information every week, as the new SAT is coming up in May, right around the corner. Thank you guys so much, and I'll see you guys next time. Take it easy.